Hello students, today we will see the theory part 40 of the chapter 8 Organic Chemistry Some Basic Principle and Techniques, in which we will cover the NCERT section 8.10. So this is our disclaimer. Now in this class your objective would be to understand the principle involved in the quantitative analysis of the organic compound. So we have already dealt with this qualitative analysis where we were concerned about the type of atoms present in the given organic compound. But in today's class, our objective would be to look upon the quantity of those atoms present in the given organic compound. So as I told you, if I talk about the specific sections of the NCERT, then it would be quantitative analysis, which is 8.10. In that, first we will see the quantitative analysis of carbon and hydrogen. Then 8.10.2, which is quantitative analysis of nitrogen. Now, starting with the quantitative analysis of carbon and hydrogen in an organic compound. Now, first notice that both carbon and hydrogen are estimated together in a single experiment. So this is efficient because these two elements are the main components of the most organic compounds. Now let's talk about the method used for this analysis. The process begins with a known mass of an organic compound. It is important to measure this accurately as the result depend on knowing exactly how much sample we are working with. The combustion takes place in the presence of excess oxygen and copper 2 oxide. So this excess oxygen ensures complete burning, so no carbon or hydrogen is left unreacted, and your copper 2 oxide is acting as an oxidizing agent. So first step is burning of the given organic compound. Now here is the general chemical equation for the combustion. C6Hy plus X plus Y by 4 O2 gives us XCO2 and Y by 2 H2O. So this equation shows that all carbon becomes carbon dioxide and all the hydrogen becomes water. Now by measuring the amount of carbon dioxide and water produced, we can calculate the original amount of carbon and hydrogen in the organic compound. Now moving on further, let us look at the procedure for this analysis. So here you can see a diagram showing the setup used to estimate carbon and hydrogen. Notice the different parts of the apparatus, each plays a specific role in ensuring accurate results. The first main step is combustion. So combustion is a chemical process where a substance reacts with oxygen to produce heat and new products. In this context, we are burning the organic sample to convert all the carbon and hydrogen into measurable gases. To start the combustion, we place the sample in a platinum boat and insert it into the combustion tube. The platinum boat is used because the platinum can withstand high temperature and does not react with the sample. So this setup ensures that the sample is exposed evenly to the oxidizing condition inside the tube. Now next we will fill the rest of the tube with copper 2 oxide or COO. So copper 2 oxide acts as an oxidizing agent, which means it helps to supply oxygen for the combustion process. Think of it as a helper that makes sure all the carbon and hydrogen in the sample are fully converted to carbon dioxide and water. So this step is important to complete an accurate analysis. Finally, we pass pure dry oxygen through the tube. So this is necessary to make sure the combustion is complete. Without enough oxygen, some of the sample might not be burned fully, so leading to inaccurate result. Now, remember, in any combustion reaction, having a good supply of oxygen is a key to convert all the elements in the sample to their oxidized form. Moving on further in the procedure. Now let's study another important part of this procedure, which is adsorption. So after combustion, the products water and carbon dioxide need to be separated and measured. So this is done by passing the gases through specific adsorbents that capture each product. Understanding this step is important because it allows us to accurately quantify the amount of carbon and hydrogen present in the original compound. First, the water produced during the combustion is absorbed by the anhydrous calcium chloride. So this is a common technique in labs because calcium chloride is very effective at removing moisture. Okay. Now ensuring that only dry gas moves on to the next stage. Next, the carbon dioxide is absorbed by concentrated potassium hydroxide. Potassium hydroxide acts as like a filter. So it specifically traps carbon dioxide, allowing us to measure how much carbon dioxide was produced. By knowing the amounts of water and carbon dioxide absorbed, we can calculate the exact percentages of hydrogen and carbon in the original sample. Now moving on further. Now let us see how we actually measure the amount of carbon and hydrogen. The general reaction for burning an organic compound which contains carbon and hydrogen is shown here. The compound reacts with oxygen to produce carbon dioxide and water. So we have already seen this equation in the previous lectures. Focusing on hydrogen first, the water produced from the reaction is absorbed by a calcium chloride tube. The increase in mass of this tube tells us exactly how much water was formed, and from that we can calculate the amount of hydrogen in the original compound. Similarly, the carbon dioxide produced is absorbed by a potassium hydroxide tube. The increase in mass here tells us how much carbon dioxide was formed, which directly relates to the amount of carbon in the compound. Now let us talk about the calculations involved. Once we have measured the increase in mass from both tubes, we can use these values to determine the percentage of carbon and hydrogen in the sample. So first we define the mass of the original compound we are analyzing. Let us call this as m naught grams. Okay. Next we look at the increase in mass of the calcium chloride tube, which we will call m1 gram. So this increase represents the mass of water produced, and from this we can find out how much hydrogen was in the original sample. Then we can similarly see the increase in mass of potassium hydroxide tube, so which we will be labeled as m2 gram. So this value tells up the mass of carbon dioxide produced, which we use to calculate the amount of carbon in the compound. Then to calculate the percentage of hydrogen, we use the formula of how much what. So percentage of hydrogen equals to 2 divided by 18 times m1 over by m0 times 100. Okay. Then here 2 is the what is 2? So 2 is the mass of hydrogen in water molecule and 18 is the total mass of water. So this formula converts our measured values into percentage of hydrogen in the sample. For carbon, the formula is percentage of C is equals to 12 divided by 44 times m2 over m0 times 100. So here 12 is the mass of carbon in carbon dioxide and 44 is the mass of carbon dioxide. Okay. So 12 is the mass of carbon in the carbon dioxide and 44 is the mass of carbon dioxide. Using these formulas, we can accurately determine the carbon and hydrogen content of any organic compound. Now we are focusing on the quantitative analysis of nitrogen in organic compounds. So let us examine the two main methods used for estimating nitrogen in organic compound. The first method is called the Dumas method, and the second method is called as the Geldahl's method. So starting with the Dumas method for nitrogen estimation. Here you can see a diagram of the Dumas method setup. Notice the arrangement of the apparatus which is designed to ensure complete combustion of the organic compound. Pay attention to the different sections of the tube as each part has a specific role in the process. Now let us talk about the combustion tube, how the combustion tube is packed. We will go through each component from left to right so you can visualize how the sample and reagents are arranged. First we have the copper oxide gauge. You can see it in the diagram. Next we add a mixture of copper oxide and the organic compound. After that we place an additional course of which is a layer of copper oxide. Finally, we have reduced copper gauge at the end of the tube. Now moving on further, what is the procedure So let us start by looking at the overall procedure for the Dumas method. Now, this was the diagram and we have already dealt with this packing of the tube. Starting with the first part, which is passing CO2 gas. By flushing the tube with carbon dioxide, we make sure that all the air and especially atmospheric nitrogen is pushed out. So this way, when we later measure the nitrogen gas produced, we know that it is coming from the organic compound we are testing and not from the surrounding environment. Now let's talk about the copper 2 oxide or copper oxide gauge. So this is a special woven material coated with copper oxide. Its main job is to help oxidize the organic compound completely during the reaction. Then the copper oxide gauge creates a strongly oxidative environment inside the tube. So this means that when we heat the organic compound with copper oxide, all the carbon, hydrogen and nitrogen in the sample are fully oxidized. Now this ensures that the nitrogen is released as nitrogen gas, which we can then collect and measure. Now moving on further in the procedure part. So let us continue. So this was our diagram. Now let us focus on the role of copper 2 oxide or CuO in this method. Okay, so we have a mixture of copper oxide and organic compound. We will look upon that. Now copper oxide oxidizes the organic compound, which means it helps convert the carbon, hydrogen and nitrogen into their respective oxides and nitrogen gas. So this is a required equation. Now moving on further. Now we have talked about this copper oxide gauge and copper oxide plus organic compound layer importance. Next, let us focus on one specific part of the setup, the section containing cores of copper 2 oxide. Okay, so we have a third layer of copper oxide, which is a cores. Thus, this region contains an excess of copper 2 oxide. Now, having more than enough copper oxide ensures that all the combustible element in the organic sample can react completely. So this is important because incomplete oxidation would lead to inaccurate nitrogen results. So we have taken 3 layers in total. And what is the need of that? The only one need of this 3 layer is to do the complete combustion. Now next, moving on further in the procedure part. Now we'll talk about the reduced copper gauge. Now, talking about the reduced copper gauge. So the main job of the reduced copper gauge is to convert any nitrogen oxides like NO or NO2 back into nitrogen. Okay, so this is important because we only want to measure pure nitrogen gas and not nitrogen oxides. Finally, the reduced copper gauge make sure that only nitrogen gas is collected and measured at the end. So sometimes due to over oxidation, nitrogen can be converted to nitrogen oxide. In that case, we are using the copper gauge, which is reduced copper gauge. Now this will ensure that the nitrogen oxide, if it is present, it can be converted back to the nitrogen. So this is acting as a reducing plate for it. Now next, moving in this procedure, what we have, so we have talked about all of these 4 parts of the packing tube. Then what about the volume measurement? So this is a key part. First, the gaseous mixture produced containing nitrogen, carbon dioxide and water vapor is passed through an aqueous potassium hydroxide solution. So the potassium hydroxide absorbs the carbon dioxide. We have already seen it, removing it from the mixture. Then next, the water vapor in the gas mixture is condensed and is removed. So this is important. We only want to measure the volume of pure nitrogen gas and not your water vapor. Then after removing carbon dioxide and water, the pure nitrogen gas is collected over an inverted graduated tube filled with potassium hydroxide solution. So this setup allows us to trap and measure just the nitrogen gas. The use of potassium hydroxide here also prevents any remaining carbon dioxide from interfering with the measurement. Next, finally, the volume of nitrogen gas is collected in the nitrometer and is measured directly. So this measured volume is then used to calculate the percentage of nitrogen in the original sample. Now let us look at how to calculate the amount of nitrogen gas collected in an experiment. Now let's calculate the volume of N2 at STP. So from the combined gas law, we know that P1 times V1 divided by T1 is equals to the P2 times V2 divided by T2. So V1 is the volume of nitrogen gas that we have actually collected during the experiment, measured in milliliters. Then T1 is the temperature at which the nitrogen was collected, measured in Kelvin. Then P2 is the standard pressure, which is 760 millimeters of mercury or mm of Hg. T2 is the standard temperature, which is 273 Kelvin. So finally, V2 is the volume of nitrogen at STP, which is what we are trying to find. The formula shows us how to adjust the collected sample to STP by multiplying V1 by 273 over T1 by T1 and by the observed pressure over 760. This gives us the volume of nitrogen as if it were measured at standard condition, making it easier to compare results. Finally, P1 or P observed is the observed pressure, which is the atmospheric pressure minus the aqueous tension. Aqueous tension is the pressure exerted by water vapor, so we subtract it to get the true pressure of the nitrogen gas. Next, here we are focusing on how to calculate the percentage of nitrogen in a sample. So we have calculated the volume. So percentage of sample is calculated as, of nitrogen is calculated as, notice here it says that 22,400 milliliters of nitrogen gas at its standard temperature and pressure weighs 28 grams. This is based on the molar volume of a gas at STP, which is always 22,400 milliliter or for 1 mole. So 1 mole of N2, which is 28 grams, occupies this volume. Notice we have a different volume, say V milliliter of nitrogen gas at STP. We can calculate its mass using a simple proportion. So mass equals 28 times V divided by 22,400. The formula, let us find how much nitrogen is present in any given volume of nitrogen and gas collected during an experiment. So finally, the percentage of nitrogen is equals to 28 into V into 100 upon 22,400 into M. Then we have talked about this Dumas method. Next, we'll talk about the Geldahl method for nitrogen estimation, which is a classical laboratory technique used to estimate the amount of nitrogen in organic compounds. Here you can see a diagram for the Geldahl's method setup. Notice the special flask called the Geldahl flask, which is designed to handle the strong acid and heat used in this process. Visualizing this apparatus help us understand each stage of the experiment. Let us break down the first main step to digestion in the Geldahl flask. So this is where we start the chemical process to convert nitrogen in our organic sample into a measurable form. Pay attention to the sequence of actions involved. First, we place our sample, which contains the organic compound we want to analyze, into the Geldahl flask. It is important to use a clean, dry flask and accurately weigh the sample for precise results. Then, next we add concentrated sulfuric acid H2SO4 along with a catalyst like copper sulfate. So the acid helps break down the organic compound while the catalyst speeds up the reaction. Then, now we have gently started heating the mixture. During this digestion process, the organic nitrogen in the sample is converted into ammonium sulfate, whose formula is NH4 whole twice SO4. So this transformation is crucial because it changes nitrogen into a form that can be easily measured in later steps. Here is the reaction that shows this transformation. So organic compound plus H2SO4 giving us NH4 whole twice and SO4. Then moving on further in this procedure. So this was our diagram. Notice the setup. So our next step is for preparation of distillation. So this is the middle step. Now let us focus on the preparation of distillation, which is the middle step of the process. After digesting the sample, we need to make the solution alkaline We do this by adding sodium hydroxide or NaOH. Here, adding NaOH, the ammonium ions in the solution are converted into ammonia gas. The chemical equation is NH4 whole twice SO4 plus 2NaOH gives us Na2SO4, 2NH3 and 2H2O. Finally, we use a gel-dal trap in the distillation setup. So this trap is important because it prevents any acid fumes from entering the adsorption flask, which could interfere with our results. So moving on further, now we have done the digestion. We have trapped also the NH4 whole twice SO4. Next is distillation and ammonia adsorption. How do we do it? After heating, ammonia gas is released. So this gas travels through the distillation apparatus. Now, next, the cold water is circulated throughout the condenser. This cools down the hot ammonia gas, causing it to condense back into a liquid form. So this step is essential because it allows us to collect the ammonia efficiently in the next part of the apparatus. Then after, the condensed liquid ammonia then enters a receiving flask that contain a volume of standard acid, usually sulfuric acid. Here, the ammonia reacts with acid to form ammonium sulfate. So the balanced equation is 2NH3 plus H2SO4 giving us NH4 whole twice SO4. So this reaction is key because it allows us to measure how much ammonia and therefore nitrogen present in the original sample. Finally, we calculate the amount of nitrogen by determining how much sulfuric acid was neutralized by the ammonia. So ammonia is acting as a base and sulfuric acid is acting as an acid using a titration which is with sodium hydroxide. So this calculation gives us the percentage of nitrogen in the sample. Understanding this process is vital for accurate analysis in both research and industry. We will continue with more detail. Now moving on further, let us start by outlining the three main steps involved in the nitrogen estimation using the gel-dal method. Step 1. Step 1, we begin by taking the known mass of organic compound. So let us call this as mass m gram. Then we add a measured volume of sulfuric acid H2SO4 with a known molarity m. Let's say we use capital V milliliters. Now let's move on to the step number 2. Here we titrate the excess H2SO4 with NaOH of known molarity m. The volume of NaOH used is V1 milliliter. Remember, V1 milliliter of NaOH of molarity m is equivalent to V1 divided by 2 milliliter of H2SO4 of the same molarity. This is because sulfuric acid is diprotic, meaning each molecule can react with 2 molecules of NaOH. This stoichiometry is essential for accurate calculation. Volume of H2SO4 of molarity m unused is equals to V minus V1 by 2 milliliters. Okay, I hope you got these 3 steps of the step number 2. Then moving on to step number 3. So V1 minus V1 by 2 milliliter of H2SO4 of molarity m is equals to 2 into V minus V1 of 2 milliliter of NH3 solution of molarity m. Next, let us recall a standard fact. 1000 milliliters of 1 molar ammonia solution contains 17 gram of ammonia, which corresponds to 14 grams of nitrogen. Now using the previous information, we can calculate the amount of nitrogen in our sample. The formula shown tells us that 2 times, so V minus V1 divided by V2. Milliliters of ammonia solution of molarity m contains 14 times m times 2. So V minus V1 divided by 2 divided by 1000 gram of nitrogen. So this is the overall formula. Now to calculate the percentage of N, what we do, we multiply the amount of nitrogen found by 100, okay, and divide the mass of the sample M. So this gives us the percentage of nitrogen, which is the main goal of the gel-dal method. Finally, the formula is simplified to 1.4 times capital M multiplied by 2. So in bracket V minus V1 divided by 2 divided by m grams of nitrogen. So this makes it easier to plug in our values and quickly find the nitrogen content. Then moving on further in the Geldal method. What are the limitations of this method? So it is not applicable to compounds with nitrogen in nitro groups, azo groups, or nitrogen in heterocyclic rings. Example, pyridine. Okay, so nitro means NO2 group. Azo is represented by single bond and double bond and single bond. And third one was nitrogen in heterocyclic compound, whose example I already told you, which is pyridine. So what is the reason behind it? The reason for this limitation is that the nitrogen in this specific form does not get converted into ammonium sulfate under the condition used in the Geldal method. Now we are going to discuss the Carius method for halogen estimation in organic compound. Let us start by looking at the setup for Carius method. So it is important to know what equipments and materials are needed before we begin any chemical analysis. Here you can see an image of a Carius tube. So this is thick hard glass tube designed to withstand high pressure and temperature. The first step is sample preparation. We take a known mass of the organic compound, weigh it carefully, and place it into the Carius tube. Accurate weighing is essential because the amount of nitrogen calculated later depend on this initial measurement. Next, we add the reagent fuming nitric acid and silver nitrate, which are introduced into the tube along with the organic compound. Finally, we will seal the tube at the neck, and it is very important for safety and to ensure that the reaction happens under controlled conditions. Now moving on further. Next, we will start by looking at the overall procedure for the Carius method. So here it was the setup for the Carius method. You can see it through the diagram. We will look at what happens during heating and chemical reaction. So this is the first step. First, the organic compound is placed in a sealed tube and heated to a high temperature for several hours. Then after, during the heating, the carbon and the hydrogen in the compound are oxidized to form carbon dioxide and water. Oxidation here means that the carbon and hydrogen gains oxygen atoms. After that, if the organic compound contains a halogen, it reacts with silver nitrate to form an insoluble silver halide, such as silver chloride, silver bromide, or silver iodide. So these silver halides are easy to separate because they don't dissolve in water. So they are sparingly soluble in water. Last, we cool the silver halide and filter it separately. So this final step allows us to see the product for further analysis. Let us look at the calculational part of Carius method for halogen estimation in the organic compound. Now, the key idea is that we use the mass of silver halide which was formed when the halogen reacted with silver nitrate to figure out how much halogen was in our original sample. First, we need to know the mass of the organic compound. We started with, let's say, call this as m grams. Next, we measure the mass of silver halide named as AgX, which is formed by the reaction. We call this as m1 gram. Remember, 1 mole of silver halide contains exactly 1 mole of halogen atom. To find out how much halogen is in the AgX we collected, we use this formula. Mass of halogen in M1 grams of AgX equals the atomic mass of the halogen times M1 divided by the molecular mass of the AgX. Then after, we need to calculate the percentage of halogen in the compound. We take the mass of the halogen we just calculated, divide it by the mass of the original sample and multiply the whole thing by 100. So this gives us the percentage composition, which is a key result in the organic analysis. So we already talked about 3 types. What are those? So we talked about, first of all, the quantitative analysis of carbon and hydrogen. Let us see how we calculated the percentage of hydrogen in compound. The formula shown here is percentage of hydrogen equals to 2 divided by 18 multiplied by mass of water divided by the mass of original compound times 100. So this tells us how much hydrogen was present based on the water produced when the compound is burned. Emphasize that water is formed from hydrogen in the compound. Then after, let us look at the formula for calculating the percentage of carbon. Here, percentage of carbon equals to 12 divided by 44 times the mass of carbon dioxide divided by the mass of this original compound times the 100. So this calculation is based on the fact that all the carbon in the compound ends up as the carbon dioxide when it is combusted. To make this calculation, we need to know what variables. So we need to know the m0, which is the mass of the original compound that we started with, and m1, which is the mass of water produced during the combustion. Finally, if I talk about the m2, so m2 is the mass of carbon dioxide produced. After that, we talked about two methods used for the estimation of nitrogen. The first one is the Dumas method, and the second one is the Geldahl method. If I talk about the Dumas method, so here is the formula used in the Dumas method. Percentage of nitrogen equals 28 times V times 100 divided by 22,400 times small m. V is the volume of nitrogen gas and m is the mass of organic compound. So we can write it here. Mass of organic compound is equals to small m, then grams. So m is simply the mass of the organic compound you started with, remember? Now, we represent the volume of nitrogen that was collected, measured in milliliters. What about the Geldahl method? Here is the formula for Geldahl method. So, percentage of nitrogen equals to 1.4 times m times V minus V1 divided by 2. All thing is then divided by small m. Here, m stands for the mass of the organic compound in grams. V is the volume of sulfuric acid, which is H2SO4. Then V1 is the volume of sodium hydroxide NaOH used during the titration step, also measured in milliliters. Then last we talked about the Carius method for halogens estimation. So here is the formula for that. It goes like the percentage of halogen is equals to atomic mass of X multiplied by m1 into m1 grams divided by the molecular mass of AgX multiplied by 100. So X is here halogen. Okay. So this was all for today's class. Thank you for your attention.